Welcome to this lesson dedicated to one of the most important areas of modern machine learning, semi-supervised learning. In the era of big data, we face a paradox. We have vast volumes of information, but only a small fraction of it is accurately labeled. It is in such cases that semi-supervised learning becomes a key solution, allowing us to maximize the utility of available data while minimizing the cost of its preparation. Today, we will examine not only the technical aspects of this approach but also its role within AI governance frameworks, including reliability, cost efficiency, and ethical considerations. And as always, at the end, I'll offer a short bonus quiz to test the knowledge you've gained in this lesson. Also, I ask you to subscribe to the channel to stay updated with future lessons. And now, let's dive into the world of semi-supervised learning. Semi-supervised machine learning is a methodology that uses a combination of labeled and unlabeled data to build more accurate and robust models. Imagine you have 1,000,000 comments on a platform. You've manually labeled 1,000 of them as toxic or neutral. Using semi-supervised learning, a model can learn from these 1,000 examples and then automatically assign pseudo-labels to the remaining comments, significantly accelerating and reducing the cost of moderation. Let's look at two foundational principles of semi-supervised learning. The first principle is the smoothness assumption. In simple terms, if two data points are very similar, they are likely to belong to the same class. For example, if your house is adjacent to your neighbor's, it's likely that both of you live in the same city. It is unlikely that a city boundary runs exactly between your houses. In machine learning, this principle is implemented roughly as follows. If two images are very close in the feature space, for instance, they have nearly identical colors, shapes, and textures, then if one of them is a cat, the other is also highly likely to be a cat. This principle enables label propagation. Having one labeled point, this is a cat, the model can confidently assign the same pseudo-label, cat, to its closest, very similar, but unlabeled neighbors. The second principle is the cluster assumption. In simple terms, data in the real world tends to form groups, or clusters, and it's best to separate these groups along their boundaries. Let's consider an example. In a city, people live in residential areas, and between these areas are parks, industrial zones, or rivers. It is logical to draw administrative boundaries through these empty or sparsely populated spaces, not right through the middle of a densely populated block. In machine learning, this is implemented as follows. If we look at all our data, for example, images of animals, we will see that they form dense clouds. One cloud will consist of images that look like cats, another of images that look like dogs. Between these clouds, there will be a region with low data density, an empty space. The cluster assumption states that the decision boundary between the cat and dog classes should pass through this empty space. This is a very powerful principle. Even with only a few labeled cats and dogs, the model sees two huge unlabeled clusters. It matches the labeled points with these clusters and concludes, aha, this large cluster is likely cats, and the other one is dogs. This allows it to classify thousands of unlabeled images based on the overall data structure, not just on the scarce information from the labeled sample. Key applications of semi-supervised learning. Cluster refinement with partial labeling. Clustering traditionally belongs to unsupervised learning tasks, but a semi-supervised approach can significantly improve its results. Imagine the task of customer segmentation for a bank. We have transaction data for millions of clients, but only for a small fraction do we know their real preferences and behavioral patterns from surveys or interviews. Semi-supervised clustering uses this partial information to guide the grouping process. The algorithm not only finds natural clusters in the data but also ensures they align with known customer traits. This leads to the creation of more interpretable and business-relevant segments. Practical implementation can include using familiar methods like k-means, where constraints such as, these two customers must be in the same cluster, or, these customers cannot be in the same cluster, guide the clustering process. The result is clusters that are not only statistically valid but also have a clear business orientation. Association rule mining. Association rule analysis in a semi-supervised context opens new possibilities for understanding hidden relationships in data. A classic example is the analysis of shopping baskets in retail. We have millions of transactions, but only for some of them do we know the purchase context, whether it was a planned purchase, an impulse buy, or a purchase for a special occasion. A semi-supervised approach allows for the discovery of association rules specific to different purchase contexts. For example, we might find that the rule bread-milk applies mainly to planned purchases, while chocolate-flowers is characteristic of impulse buys before holidays. Algorithms create context-dependent association rules, allowing for the consideration of differences in user motivation and behavior and providing more accurate recommendations. This is especially important for personalized recommendation systems, where understanding user motivation is critical for success. Fraud detection is an ideal application area for semi-supervised learning. Fraudulent transactions typically make up less than 1% of the total volume, creating a severe class imbalance. At the same time, known fraud cases provide valuable information about patterns of suspicious activity. The semi-supervised approach begins by analyzing known fraud cases to identify characteristic features, unusual transaction times, geographical anomalies, spending patterns that differ from a user's normal behavior. These features are then used to analyze unlabeled transactions to detect similar patterns. The uniqueness of this approach lies in its ability to detect new types of fraud. Traditional systems are good at identifying known schemes but may miss new methods. Semi-supervised learning, by analyzing the overall data structure, can identify anomalous clusters of transactions that do not match normal behavior or known fraud types. Exploratory data analysis in this context includes continuous monitoring of changes in transaction patterns, detecting data drift, and adapting the model to new types of threats. The system can automatically flag suspicious transactions for manual review, thus creating a closed-loop learning cycle. Semi-supervised learning is not a single algorithm, but a whole family of approaches. To understand how they work under the hood and what governance risks each one carries, let's examine three main groups of methods. Iterative approaches. These methods act as wrappers around standard machine learning models, incrementally improving them using unlabeled data. Self-training. The key idea, a learner that sets its own tasks. The model uses its own most confident predictions for self-training. Imagine a medical student. First, they learn from a small number of examples shown by a professor. Then, they independently study a vast library of anonymous case studies. The cases where they are absolutely confident in their diagnosis are added to their notebook as new, verified examples, and they remember them, becoming more experienced. A base classifier model is trained on a small set of labeled data. After training, the model is applied to a large set of unlabeled data. The predictions in which the model is most confident are selected. These predictions are called pseudo-labels. The selected data with pseudo-labels are moved from the unlabeled set to the labeled set, on which the model is retrained. The process repeats until all data is labeled or a stopping criterion is met. The key risk for AI governance is error accumulation. If the model makes a mistake with high confidence early on, this error will enter the training set. In the next iteration, the model will train on this error, which can lead to even more of the same mistakes. This is the echo effect or bias amplification. Our task is to implement strict control over the confidence threshold. It is necessary to continuously validate the quality of pseudo-labeling on a holdout set and have a mechanism to detect and correct cascading errors. Co-training. The main idea is this: two experts who teach and check each other. Two different views of the same data are used. Let's imagine two detectives investigating a case. One analyzes only the textual witness statements. The second analyzes only the physical evidence, photos, fingerprints. When the first detective identifies a suspect with high confidence based on the statements, they pass this information to the second. The second detective uses this clue to take a fresh look at the physical evidence. Mutual learning increases overall confidence. The data must have two independent feature sets. Imagine sorting fruits by two independent criteria, shape and color. We have two models. The first learns by shape, round, oval, cone-shaped. The second learns by color, green, yellow, red. And each of them has only 10 labeled examples of apples, pears, and bananas. The shape model analyzes 100 unlabeled fruits and selects 20 in which it is particularly confident, for example, perfectly round apples. We add these 20 pseudo-apples to the training of the color model. Now it has 30 examples of apples by color, and it can distinguish them more accurately from others. Then the color model finds its 20 most confident examples, say, bright yellow bananas, and passes them to the shape model. In this way, the models teach each other step by step. The key risk here is feature dependence. The method works only if the two views of the data are conditionally independent. If they are highly correlated, the models will not teach each other anything new. Most likely, they will just reinforce the same errors. Before implementing co-training, a statistical analysis must be conducted to prove, or at least justify, the independence of the views. Generative approaches. These methods try not just to separate the data, but to model its internal structure and how it was generated. The main idea is to understand how the world is structured in order to classify its components. The model learns the joint distribution of all data and uses labeled points to give names to the discovered clusters. As a simple illustration, imagine an art historian who wants to learn to distinguish Monet's paintings from Renoir's. Instead of just comparing pairs of paintings, they study dozens of works by both artists to build a holistic understanding of Monet's style and Renoir's style in their mind. Unlabeled paintings help them better understand the nuances and boundaries of each style. The algorithm assumes that the data consists of several clusters of a certain shape, for example, an ellipse or a circle. It uses all the data to determine the centers and shapes of these clusters. Then it uses only the labeled data to assign a label to each found cluster. This is a Monet painting, this is a Renoir painting. The key risk is a model data mismatch. These models are powerful, but their strength is based on strong assumptions. They assume that data in the real world is structured according to certain, often simple, rules. The real world is much more complex. Using the art historian analogy, imagine they decided that all paintings are either Impressionism or Cubism. When they encounter a work by Salvador Dali, Surrealism, they will not be able to recognize the new style. Instead, they will be forced to classify it as either Impressionist or Cubist, which would be a gross error. Our task is to ensure that the chosen model does not impose its distorted worldview on the data. The team must justify why their model's assumptions, for example, about the shape of clusters, are applicable to our business. Ask, what will happen if new, unforeseen groups appear in the data? Will the model be able to see them, or will it continue to make mistakes? The decision to use a generative model with its assumptions must be documented and justified, especially if important business decisions depend on it. Graph-based methods. These methods explicitly use the smoothness assumption and the cluster assumption by representing the data as a network, or graph. The main idea, labels propagate through connections, like rumors. Similar objects are connected, and the label flows from labeled objects to their unlabeled neighbors. Imagine a social network of music lovers. You know the musical tastes of 10 people. To predict the tastes of the others, you look at their social circles. If a person is closely connected to 5 known rock fans and no one else, they likely enjoy rock music too. The information spreads further through friendship connections. A graph is created where each object, for example, an image, is a node. Nodes are connected by edges if they are similar to each other. The weight of the edge reflects the degree of similarity. Labeled nodes radiate their label. This label spreads along the edges to neighboring nodes, weakening with distance. The process continues until each node receives a final label based on the balance of influence from all its labeled neighbors. The key risk is sensitivity to the similarity metric. The entire result depends on how we define the similarity of objects and construct the graph. An incorrectly chosen metric will lead to the creation of wrong connections, and labels will leak into the wrong clusters. Bridges between clusters can completely spoil the result. The similarity metric is a critically important parameter that must be transparent, justified, and validated. It is necessary to control the structure of the graph and be prepared for the fact that small changes in the data can greatly affect the result. Semi-supervised learning raises unique ethical questions related to the automatic generation of labels and the potential amplification of existing biases. When a model creates pseudo-labels for unlabeled data, it can inadvertently amplify the biases present in the original labeled data. Automatic pseudo-labeling can lead to several forms of harm, especially if errors propagate uncontrollably. It is important to understand the different types of potential harm that can arise. Allocative harm is the unfair distribution of opportunities or resources. Consider a credit scoring system where a semi-supervised model has incorrectly pseudo-labeled data about borrowers from certain social groups. If the historical data contains systematic biases against certain demographic groups, the model might not only reproduce these biases but also amplify them by applying them to a large volume of unlabeled data. As a result, the system might incorrectly deny loan applications from representatives of vulnerable groups or offer them less favorable terms. Representational harm occurs when AI reinforces stereotypes and distorts the image of a certain group of people. This is especially evident in natural language processing systems, where semi-supervised models can misclassify texts written in certain dialects or using culturally specific vocabulary as toxic or inappropriate. Such erroneous pseudo-labeling effectively solidifies negative associations with certain linguistic communities and can lead to their discrimination on digital platforms. Quality of service harm occurs when a system works reliably only for some users, creating inequality in the quality of services provided. A classic example is facial recognition systems, where semi-supervised models, trained on imbalanced data, may perform excellently at recognizing white men but regularly make mistakes when recognizing women or people with darker skin. These errors are then amplified through the pseudo-labeling mechanism, creating a vicious cycle of inequality in service quality. These categories of potential harm are described in C-SET's harm taxonomy, which is an important tool for systematically assessing the risks of AI systems. When designing semi-supervised solutions, it is useful to rely on this framework as a tool for preliminary assessment of potential risks and unfairness. Ensuring fairness requires active monitoring of the model's results across various population subgroups, taking into account all three types of potential harm. Fairness metrics should be tracked not only for the labeled part of the data but also for the automatically labeled data. This includes analyzing equality of opportunity, monitoring the representation of different groups in the pseudo-labeling, and assessing the quality of the system's performance for all user segments. Transparency in the decision-making process becomes even more critical in semi-supervised systems. Users and regulators must understand how the model uses unlabeled data and what impact this has on the final decisions. Documenting the pseudo-labeling process, including data selection criteria and confidence thresholds, becomes a mandatory element of responsible AI. Successful deployment of semi-supervised learning requires a systematic approach, starting with a thorough analysis of the available data and business goals. The first step is to assess the quality and representativeness of the labeled portion of the data. A small, but high-quality and balanced sample of labeled data is often preferable to a large volume of data of dubious quality. The choice of a suitable algorithm depends on the specifics of the task and the characteristics of the data. For structured data with clear features, graph-based methods work well. For texts, iterative approaches that transfer labels between similar examples work well. Monitoring the performance of semi-supervised systems requires special metrics and approaches. Traditional metrics of accuracy and recall should be supplemented with indicators of pseudo-labeling stability, consistency between different approaches, and sensitivity to changes in the data. An important aspect is model lifecycle management. Semi-supervised systems require more frequent retraining and updating compared to traditional supervised models, as they actively adapt to new data. Automating this process, including detecting the need for retraining and validating new model versions, is critical for maintaining high system quality. Friends, and now it's time to test your knowledge in practice. For this, we have prepared a special bonus quiz. Which principle underlies the assumption that similar objects belong to the same class? What risk is characteristic of iterative self-training? What makes the co-training method unique among iterative approaches? In which case are graph-based methods most appropriate? What does representational harm mean in the context of semi-supervised learning? Why is it important to document the pseudo-labeling process in semi-supervised systems? And now you can pause and answer all 6 questions on your own. Write the results in the comments, and we will discuss them. The correct answers, as usual, will be published in our Telegram channel. The link to the Telegram channel will be in the description. Today, we learned how semi-supervised learning helps use unlabeled data to build accurate and robust models. We examined the key methods, risks, and ethical aspects, as well as practical steps for implementing such solutions in real-world projects. Thank you for your attention. Good luck with your study and application of these ideas. And see you in the next lesson.